Hi, my name is Kiran Baburaj. Welcome to Career Campus Pro YouTube channel. Welcome to our exploration of heap data structure. In this video, we will focus specifically on binary max heap, a specialized tree that's optimized for finding the maximum value in constant time. Let's start with an empty heap. Notice how it's arranged like a tree. It's a complete binary tree, which means all levels are filled except possibly the last one, which fills from left to right. Now let's see what makes heaps so special by inserting some values. The magic of heaps comes from how they maintain their structure during insertions and deletions. We start by inserting 15 at the bottom of our heap. Since it's the first element, it becomes our root node. Now we insert 45. In a max heap, the parents must always be greater than its children. Since 45 is larger than 15, we need to swap them to maintain the max heap property. This process is called heapify. When we insert 10, it starts at the bottom. But since it's smaller than its parent, 45, it stays where it is. Perfect. Next we add the element 25. It's larger than its parent 15, so we swap them. But it's still smaller than 45, so it stops there. Next we insert 50. It starts at the bottom, but it quickly swaps 25 and also swaps 45 all the way to the top, because 50 is our new maximum value. And in the max heap, the largest value always sits at the top. Next we add 20. We place it and compare it. It's larger than its parent 10, so we swap once and then stop. Finally, we add 30 and we compare it with its parent's 20. It's larger, so we swap it and the heap property is properly maintained. Finally, we have inserted all our nodes to our heap. We can notice that it is maintaining the max heap property. Parents are always greater than their children. Now let's move on to max heap deletion, the secret behind priority queues and sorting algorithms. Let's watch what happens when we need to remove the maximum element. This is where the real magic happens. We identify the maximum value, which is always at the root of our max heap. In this case, it's 50. But we can't just remove it and leave a vacant space. That would break our heap structure. We take the last element of our heap, 10, and move it to the root position. This maintains our complete binary tree structure. But now our heap property is violated because 10 is smaller than its children. We compare 10 with its children and swaps with the larger one. This case 45. This process continues with that position until it finds its proper place in the hierarchy. So we compare the current position of 10 with its children. So we find 25 as the largest element and swap it with 25. Now our root node deletion is completed and our updated root node is 45. With each deletion, we are effectively extracting the elements in decreasing order. This is actually the foundation of heap sort, one of the most efficient sorting algorithms with guaranteed n log n performance. This self-balancing property is what makes heap so efficient for both insertions and deletions. Both operations run in logarithmic time, regardless of how many elements we have. So deletion in a heap is quite simple. Just remove the root, that is the maximum element in a max heap, and replace it with the last element and heapify down to restore the heap. That's it. Now let's move on to the heap implementation using Python. Let's start by defining our max heap class. We begin with a constructor that takes the maximum size as a parameter. We will initialize three important attributes: m size, the maximum capacity of our heap; size, to track the current number of elements; and heap, an array initialized with zeros, which store our values. In the insert method, first we check if there is a room in our heap. If we have space, we add the new value at the end of our active elements. Then we heapify. This process maintains the heap property by comparing the newly added element with its parents. If the child is greater than its parent, we swap them and continue moving up the tree. This ensures that the largest element bubbles up the root. Now let's look at the max heapify method, which is essential for maintaining the heap property when removing the elements. This method takes a position and assumes the current node is the largest, calculates the indices of left and right children, checks if either child is larger than the current node. If a larger child exists, swap with that child, then recursively continues the process downward. In the remove method, we store the root value, that is our maximum, replace it with the last element in the heap, and reduce the size by 1. Call the max heapify to restore the heap property and return the original root value. We also have a getMax method that returns the root element if the heap isn't empty. Heaps are a powerful tool in our algorithmic toolkit. Use them whenever you need efficient priority management in the applications. Whether you are implementing the priority scheduler or digest Carter's algorithm, or just need to maintain a collection where you frequently access the maximum or minimum element, a heap is often an ideal choice. If you found this video helpful, please don't forget to like and subscribe. Happy coding, thank you.